One circuit. One circuit. It's one circuit that is a single circuit. Everything's connected together. So y'all are looking at a circuit. Now the way you solve it, you might solve it as two circuits, yeah. But technically that's one circuit, right? You understand? It's just that we go through two stages. These parts over here. What? Okay, there we go. That makes sense now. No, that's what Milton was talking about, and then you came over here and said this circuit over here. So you shifted gears on me. I I don't know what you mean. Well, let me wait. Let me get it. Let me get it up. Let me see if I've got one for that worksheet. So when us trying it, because one thing, color code is we use a color code for resistors. I go over there and get an inductor, and you're gonna think it's a resistor, but it's an inductor. So we use a standard color code for a lot of things, right? Like transistors, we see a 3-lead device. Is it a transistor? Now we don't know, right? It could be. It could be a regulated power supply. It could be a triac. It could be an SCR. So what they've done is they came up with standard designators. That one of them you've been using your whole tenure here at the college, called R. So if you see R beside a component, what do you know it is? You know it's a resistor, right? If you see L by a component, it means it's an inductor. So they'll say L1, L2, L3. If you see C by a conductor, it means it's a what? Capacitor. If you see T by something, it means it's a transformer. So transformers have been out. So we got T1, T2, T3, right? You understand? So when it came to transistors, they couldn't use T. So this is when they start using other letters of the alphabet, right? You understand? And so Q is the designator for a transistor. So if you're looking at a diagram, or you're looking at a diagram on your schematic, all your transistors are going to label Q, right? You understand? And then when you're trying to find these on the circuit board, you're looking for Qs. Well, let's see if we see some Q. Yeah, so here. So we're looking at this power supply that we was looking at. This is a 10-volt 5-amp power supply. When I start looking at these components, okay, I see C1, C2, but I look at this guy right here. Can y'all see what it's designated? Let me bend it out of the way. Oops, wrong way, Rich. No, it's not. Q2. So that tells me this is not an SCR. This is not a triac. This is not a voltage regulator. This is a what? A transistor, right? We can't see this when it's covered up with the heat sink thing, but this right here is designated Q1. You can't see it. And what's nice? So that's a transistor right there, guys. But how do I know, even though it's covered up? Well, I know it's got 3 leads, but the solid state components that could be would be quite as long as it fits in that package, right? You understand? So if I see a Q, and there's a T1 right there beside the Q1, if I can get this, can y'all see the T1 and the Q1? Well, Q1 means this right here is a what? A transformer. It's not an inductor. If this was an inductor from the outside, inductors are nothing but coils of wire. So your big ones, you're going to actually see them. They're going to look very similar to a transformer. But you can tell them apart because an inductor usually only has 2 leads coming out. A transformer is going to have a minimum of 4, right? 2 for the primary, 2 for the secondary. But I can't get to that because it's mounted and covered up with this shield that's also serving as a heat sink. But I know it's a transformer because it's using the designator what? T, right? What is this guy right here? This guy looks almost exactly the same, but it's got a designator. If I can turn it so you can see, oh, there it is. It's got a designator of L. So this is an inductor. So it's in there for filtering, right? You understand? So that's what these designators mean, and y'all really need to learn them because it tells us a lot as far as, because so on the schematic, what they're going to do is they're going to designate it when they draw the symbol. They're going to give it the same designator name as it's on here, right? So now I see T1 on the schematic. It might be on the left, and the problem we have is that when you do these, and I've seen this over and over and over again, where students try to wire a circuit that looks like the schematic. So everything's arranged in the same way. You're not going to see that in real life. What they're trying to do is make their thing as small as they can possibly make it, and they got to really watch out for crossing lines. You can't cross two lines on a printed circuit board. So you might have, on your schematic, R1 might be over here, and then you look at your circuit board, R1 might be down at the bottom, right? You understand? And so so a lot of times, guys, you have to scan for quite a while to see it. So this is a really, really good example. F fuses. It looks like the fuse in this might be, well, I don't know. It's only 1.2 amps or 1.5 amps. This guy usually are detonated F, right? Okay. Are we okay? So I don't see any more designators that we didn't talk about. Integrated circuits, this guy's using one of the designators. They call them ICs, but normally what they try to do is they try to designate with one letter. So every once you'll see people say IC for integrated circuit, but most of the time it's going to be called U, U1, U2. So if I looked at this thing right here, and it had U1 on it, then this wouldn't be a transistor. It would be an integrated circuit that only needed 3 pins to the outside world, right? You understand? Like a voltage regulator. Of course, this is a potentiometer. This, they got it labeled CR1. I'm almost sure this is the rectifier bridge right here. I'm not sure. I'd have to look, but and that's all I see. But what you do on your schematic, even though they don't use non-standard designators, they look at this. I just saw that. Can y'all see this little tiny guy right here? There's a transformer, yeah. And you can actually, what's nice is you can actually see the windings on this little transformer. But yeah, so there you go. I hadn't fired this thing up yet to see if it works. We've had it for a long time. I need to, because a 5-volt 10-amp supply is. So what are we given on this guy? We're trying to calculate this resistor right here. We're trying to calculate this resistor right here. Huh? We're trying to calculate R4. Yeah, that's the guy right there. 3 volts. How many of y'all caught that? Just for you. It wouldn't connect to my computer, but I finally figured that out. So 3 volts. Okay, 3 volts right there. So what's that going to tell us? Well, we don't know, because it's got a transistor in there. The transistor's dropping 3 volts. The transistor's not the transistor. We don't know what the transistor's dropping, right? You understand? I'm sorry. We know the transistor's got to be dropping 3 volts. Why do I know the transistor's got to be dropping? This guy, we're working on this one right here. Q. Yeah, you got 3 volts on the collector. So if you got 0 volts on the emitter, you got 3 volts on the collector. It means that transistor's got to be dropping 3 volts. So I can't use that transistor right now. Well, what else? What do I know? I know this guy right here. This guy right here is 2.3 volts. I know now, right? I know that, right? Yeah, because I got 0.7 on the one and 3 on the other side of the resistor, and then the emitter's connected to ground. Okay, so I know how much voltage. I know how much voltage R2 is going to drop. Right. So this is going to drop 2.3 volts. Right. Okay, so where do we go from here? How can we find IC? So we can come over here if this is a saturated. This is not a saturated switch, guys, but it's controlled in our saturated switch, right? Y'all understand that? Yes or no? Huh? Okay, that makes sense. Y'all didn't tell me that. So we know this guy, if these are saturated switches, this guy's going to drop what? We know it's got to drop 12 volts at 1K. So Y would be equal to what? 12 milliamps. We okay? And now we can find IB, right? So I'm going to take 12. I'm not right. I'm just writing. When y'all do y'all's, you got to come over here and say, well, so this would be what do we call this right here? We call it IC sat. It's just not net. It's a saturated collector current, right? Everybody okay? And so what we'll do now is we'll deal with IB sat, which is how much base current would be required to saturate this. Yeah, we're right here. I don't know what you mean by the Q2 side. It's the base side would be more correct. So you could say, well, it's the base resistor. It's the base resistor for Q2. So this right here is the base resistor for this transistor right there. Is that okay? So why are we going to do this? Well, I'm going to take IC, which is 12 milli, and then I'm going to divide that by 50, right? Minimum beta. Huh? What's that? Okay, good. Then I'm going to calculate R2 by taking 2.3 volts and divide that by 240 micro. 9.1. That's right. That's what he was saying. He left all his calculated, which he knows he's not going to do that on test, right? And here it's not getting the answers according to what the key says. Here it's just attempting to work, right? All your circuits attempting them. So even if it takes going back and re-listening to the lectures and stuff like that, that's what we're looking for. So, and then what we do now, I come over here and I put down, so there's 4 circuits on here. So, I put down 1 over 4, 2 over 4, 3 over 4, whatever, and that's the grade you get on the ones you attempt. And then I give you the key, and then we do what? Then we go back and work the ones y'all won't work. So what do we need to do now? Yeah, I didn't get the numbers. This is Q2. For some reason, my Q numbers didn't copy over. This is Q2, and this is Q1. Yes, 250 micrograms. Oh, I don't know. So what we're working on here, we're doing 12-minute lap. So this is definitely Q1, right? This is Q1, and this is the saturated current. So, yeah, but what we didn't do is we didn't compensate for this current with this chosen resistor. So this is what we calculated, right? You understand? And then that came up to be, what did it come up to be? 9,005. Okay. But what's happening is we didn't use that, so we used a 9.1K. So right? IR2. I'm sorry, IR2 is going to be equal. It's still got to drop 2.3 volts, but it's going to drop it at 9.1K. So that's what comes up to be 253 microamps. So what you got to do is what did we calculate? I'm sorry, 9,583. And we can't use that. Why can't we use that? It's not a standard value. So this value would give us 240 microamps, right? You understand? I is equal to V over R. But we didn't choose 9. We're not using 9,583. We're using what? 91K. So now what I've got to do is I've got to come back and figure out, okay, if I drop 2.3 volts over 9.1K, what is the base current going to be? Not calculated what it's actually going to end up being. So that's exactly right. No, it's still Q1. You're thinking about this. This resistor belongs to that transistor. This resistor is controlled by that transistor. So this is just like an amplifier, and I bring an input over here. And this input right here has got a resistor in it, and I got another amplifier over here, and you're trying to tie this resistor to that amplifier. All this right here belongs to Q1. All this right here, I'm a Q2. All that right there, oh, I know what you mean. I got it backwards on here. So this should be Q2, and that should be Q1. It finally popped in my head. Yeah, the heading. The heading's wrong. All the formulas are right. It's the heading's wrong. Thank you. Thank you, Milton. True, right. So now, sometimes I'm bullheaded. Sometimes I'm bullheaded, guys. Like some of y'all. Thank goodness Milton is. So. Yeah, because all the formulas say Q1, and that's what he was saying, and I wasn't hearing that. I wasn't seeing the heading up there because he had marked out it, so that was my fault. Okay, so we okay? And this is where I think my worksheet runs into a little problem. Oh, okay, this flows when this guy here turns off. Okay. So what we have now is we're calculating the size of this resistor. So I got 3 volts right there, right? Y'all understand? So you were right. If 3 volts is dropped there, this transistor is what? Off. Okay. Then that means this resistor right here has got to drop 9 volts at what? That current right there. So our current path for our base, guys, is this path right here. It comes up, goes down, and it goes up this way. Okay. So, but we don't need to take out the 0.7 because I've given you the voltage at point A. Right? You understand? Okay. So what we got to do is find a resistor R1 would be equal to 9 volts divided by 253 microns. Yes, yes, because I can't say 7/10 there because that's 3 volts, right? That's what I get to. Yeah, but you know what you've done wrong, right? Okay. So what size we got for R1? What's that? Okay, 33 kilo ohms. So what we're going to do is we're going to increase our base current, which don't hurt. All we got to do, so the actual base current, this guy here is going to drop a little more voltage, right? This guy here is going to drop a little less, but still the calculations are going to work out for these sizes. So we're going to use a what, 3.3? So now we can say, okay, my base current is actually, uh, so this guy's not going to drop 9 volts, right? It's going to drop a little less than 9 volts. This guy, and this right here would probably still be, this guy here is going to drop a little more. Base current's going to go up, but once the transistor's saturated, it's what? It's saturated. Okay, guys, what we're going to do is we're going to cut this transistor off. This transistor here is going to cut off when this transistor right here cuts on. So what's going to happen when this transistor cuts on and saturates, that's going to bring 0 volts and put it right there. 0 volts is right there, right? You understand? Everybody okay? So that 0 volts, I have no base current. This guy here is no longer going to drop 9 volts. When it's saturated, it's going to jump up to 12. Because now it's dropping all the voltage, right? You understand? So what size would we use for R2? Well, we got this resistor right here. We calculated R1, right? You understand? And we're using a 9.1K. How much current would flow for 9.1K? Oh, I'm sorry. What's R1? Okay, thank you. I just looked over and saw numbers. I guess I should pay more attention. 33K. So IR1, which I'm sorry, so IC sat, we're calculating the saturated current, would be equal to 12 volts divided by 33K. What do I have applied right there? It was 9 volts when it was cut, when Q1 was cut off. When Q1 turns on and saturates, that means this right here is 0. So this guy saturates, so this guy drops no voltage. That brings that 0 volts and puts it right at the bottom of that resistor. So I got 0 volts right there. I got what up here? 12 volts. And this is really common, the way we use to switch a transistor off and on. So what we're doing is that there was one of our circuits that was drawn like this, where I came over here and I had some type of load. And then I came over here, and I came over here and I put a resistor right there. And then I put a switch right there. And what do we do when this switch is closed? The transistor cuts off. When the switch is on, when the switch is off, this transistor cuts on. What we're doing here for this switch right here is we've moved this resistor right there, and then this resistor would be the resistor for this transistor right there, right? You understand that? So when this guy cuts on, that puts 0 volts right there. If that puts 0 volts right there, what does this transistor do right here? It has no base voltage. So what would it do? It cut off. And this is really, really standard. So now I'm turning this transistor off and on electronically. Who has to move that switch? You do, right? What moves this switch right here? 12 volts. Where does the 12 volts come from? Well, it might come from another transistor. It might come from another circuit, right? You understand? It might come from me matching this little old dang button right here on my power supply, right? No, our four is, if it's off, then this is 0 volts. It can't be dropping to 12 volts because that's the only thing that would turn it off. If our four dropped 12 volts, that's going to be a ton of current pouring into Q1, and Q1's going to saturate. So if I had 12 volts dropped across R1 or 11.3 volts dropped across R1 and all the voltage was dropped across the transistor, I'd take transistor out and throw it away. Because if you have base current, this transistor, if you have any base current at all, guys, this transistor is either going to be in the saturation or it's going to be in the active region. It's not going to be off. It's not going to be on. So that's why we say right here I can put what? I can put two things right here. I can either put what? Ground, or I can put what? 12 volts. If I put ground, yeah, so I put ground on there, the transistor turns off. Right? If I put 12 volts on there, it turns on. So we're going to say R4, but we're going to have to size R4 to allow enough base current to saturate the transistor. Right? You understand? So we know this base current right here, right? I mean, this current over here to saturate it. What's required to saturate it over here? 12 divided by 33K, guys. So what we're doing over here, guys, is we're controlling 12 milliamps over here with what? 363 microamps over there. And so and of course, in what we're doing, and we add the other transistor, we get gain out of that, right? You understand? So here I go from 363 microamps, which is not what it's going to be because we hadn't sized the resistor. Are we okay? Okay, so what size of the resistor? This guy's going to drop what? 11.3 volts. Or 4 is going to drop 11.3 divided by 363.6 micro. Oops, don't pay attention to that error, guys. I want to confuse you. Well, then the key might be. What's that? 11.3. R4 is 11.7 over 5.5 micro. Well, we'll have to do the math. It might be, it's supposed to be 11.3, but when I typed it, this thing don't do math. I have to key every bit of this in, by the way. And we came up with 363, but somehow I got 5.5 micro. So the first formula is wrong, right? RC-SAT Q1. Oh, I'm sorry, Q1. So it's right. So the first one, Q2, right? Q2's on the left. And this last equation, that's supposed to be a 2 also. Okay. So 12 milliamps, 249.1K. Are we so far? Okay. And then on the other one, it's 33K. We got that right. 273 microamps. So that's a problem there too, right? I see set Q1 is supposed to be what? 12, right? And then we take minimum beta 273 divided by, oh, so we didn't do that, guys. So I used this right here right off the bat, but nobody caught me on that either. So we should have took this and divided it by what? Beta, right? So so this is supposed to be 12. This is supposed to be 233 divided by 253. No, R1. VR1, where's VR1 at? Did I erase it? Yeah, R1 is supposed to be 12 when we calculate this saturation, right? 33K, so what should that current be? You'll see where I'm at? Yes or no? Okay. Yeah, so the key, I don't know why we ain't caught that. So the key is wrong. Let me, what I need to do is bring up the key. And show you where we're at. Okay. And I'll go in, okay. So we're looking at this guy right here, okay. All right. Are y'all listening up? Okay. So this right here, when this transistor cuts on, R1 drops all the voltage. Well, down here at my key, I've got what? 9, and it's supposed to be what? 12. Okay. And this is Q2. When I put 12, so what we're trying to do is we're using Q1 to turn Q2 off and on. Okay. So what we did is we came up with the when we turned this thing off. Let me go back to my PowerPoint. So when I go back to so that means to turn this transistor saturated, we've got to have a voltage at point A. Okay. So we established, and this is what you would do if you were going to design it. We'd establish 3 volts. We know we got to have more than 7/10, right? And we've got to have enough where we can control it so this resistor will drop a voltage. Okay, so how do I get 3 volts right there? When we calculate this whole thing, this is the path that the current is flowing right now. It's coming up here, going this way, and the sums of the voltage drops have to equal to applied voltage. How much current flow is through this transistor right there? Q1. None. It's cut off. So when I cut this transistor here off, we're going to have this path right here. It's going to have to turn on and saturate this transistor. This transistor here is going to turn on. So how do I turn this transistor on? Well, when I come over and put 12 volts right there, this transistor turns on and saturates. If it turns on and saturates, guys, and that's what we're doing because we got to put 0 right there. The only way I could put 0 volts right there, Well, we got to put less than 7/10 of a volt or less than 500 millivolts, right, to turn it off. Well, if we put it 0 volts there, we're guaranteed to turn it off. So what I'm doing, guys, is I'm coming over here and doing this. Let's do it with resistors. So here's a resistor right here. Here's a resistor right here. Here's this transistor over here. And what I'm doing, guys, is I'm putting a switch right here. And this switch right here is connected to circuit common or ground. And I've got 12 volts up there. So when this switch is open, it allows current to come up here and flow up this path right there. When this switch right here closes, guys, there's 0 volts right there. It's all over the place. So there's 0 volts right there. So how much current flow is this resistor right there? I got 0 volts right there. I got 0 volts over there. How much current flow is through this path right here? 0. Now I got 0 volts sitting at the bottom of that resistor. I got 12 volts at the top of that resistor. When I saturate, that resistor is going to have to drop 12 volts, right? You understand? We calculated it to give us the current to saturate this transistor Q2 when the transistor's turned off. Now we got to figure out what collector current is going to flow through Q1 when it's saturated. So how do we figure that? Well, we know R1, right? We know R1. What size is R1? So we say IC sat Q1 is going to be equal to 12 volts divided by what? 33K, because that's the size that we chose. So when it's saturated, it's going to drop all the voltage, so we get 0 up on the base of the other transistor and make it turn what? Off. When this guy here is on, we got 12 milliamps, right? You understand? Milliamps. But what we're going to be doing is controlling this with like 6 microamps. So we'll see what current gain we get out of this thing in a second for the entire circuit. So if this guy here does this, then IC sat for Q1 to saturate this guy, right, would be what? So you understand, Anthony, makes sense now? Yes. So what would it be? What's that? Oh, crap. Oh, I erased it. Let's see, IC sat Q1 equals 33, sorry. Yeah, I need to correct the key, so the key was wrong. Y'all need to give yourself a pat on the back and tell me how many times we use that key. And I don't know how I got. That's where people just sit back there and go, okay. 12 volts divided by 33K. What'd y'all say? 363. Okay. And then IB sat calculated Q1 would equal to 11.3 volts divided by 364. I'm sorry, would be equal to, yeah, I did it again. IB sat would be equal to 364 micro divided by 50. You know, 7.28 micro or 7.3 micro, right? Okay. Then R2, I'm sorry, R1, I'm sorry, R4 would be equal to 11.3 divided by 7.28 or 7.3 micro. You can round up, but don't round down because we're trying to move away, right? So what's R1 equal to? R4 equal to? Sorry, guys. 1.5 meg. That mega ohms. And then what should we do? Go down at least one, right? So what's the next standard value be below 1.5 meg? Okay, so cheap, right? So 1.3 meg times 1.05. What does that give us? We're probably going to have to go down one more, guys, because it fell right on the resistor. Okay, so that's good then. So here we'd use a watt, 1.3 meg. So what I'm doing is I'm coming over here, I'm getting 12 milliamps out, 12 millirich, divided by 7.2 micro or 7.3 micro. So what's our gain of the circuit going through two transistors? And that's rough, huh? No, you can't take. We're calculating the current gain of the circuit. So our output current is 12 milliamps. Our input current is 7.2 microamps. But it's actually more than that because we didn't recalculate it for the standard resistor, but we're just looking at this anyway. 7.3 microamps gain of what's driving this thing and what we're actually driving, right? So every transistor you go through, you get a current gain out of it if you design your circuit right. So we're getting over 1,000 gains. So whatever's driving this thing, right, is only required to. We could set up a touch pad on this, very easy, guys, and just touch between ground and me, and it would saturate or turn a light on or something. Because my body can provide 7.2 microamps, right? You understand that? So we could. This is almost nothing. We could probably stick an antenna up on the air and pick up radio stations, but it's saturated switch, right? So we wouldn't do us much good. But so this is what you got to understand is what we do is we can take it through what we call stages. So this would be a stage right here of amplification, and this would be a stage right here. So this would be a two-stage circuit. And you'll find that out in amplifiers where we go through multiple stages, 6 or 7 stages between your CD player, the input to your CD player or your radio, and the output to your amplifier. I mean, to your speakers. Like where do we put the balance at? Where do we put the fade at? Where do we put the front rear balance at? You can't put it out there where you got these 100-watt speakers, right? You understand? Because you wouldn't have a little old push button. So these are going to be way back in the front end. So most power amps are divided into two big categories. We have the preamp, and then we have the power amp section here. All your controls are going to be somewhere in your preamp, right? You understand? And then the power amp, you turn that sucker loose. You know, some of them you can actually split the preamp and the power amp out of there. So you can take the output of your preamp and run it into like a big power amp. And some power amps takes the output of your power amp. So some power amps treat your whole radio as a preamp. So yeah, we could. So let me while I got this open. So y'all help me out, guys. Let's go back and make our corrections. So this down here is supposed to be Q2. Okay. And then IC, so IC sat Q1, what's it supposed to be? We're going to change this. Which changes this to 7.1. I think I probably did this math right. I just put the wrong number right there. So we computed a what? A 1.5 meg. And we ended up using a 1.3. Okay, so that's good. Which one you want? Oops, let me make this bigger so we can see this. Huh. Oh, it kept what was on before. There's the other one. Okay. So that's the international symbol of a relay coil. Okay. And first thing we need to do is calculate the amount of current that's required to turn this relay coil on. And so what we'll do is we'll take I is equal to V over R. So I would be equal to 6 divided by 375 ohms. And that would give me the current. And a lot of relays, guys, are rated in ohms. They're not rated in current. They're rated in ohms, which is good because you can put your ohm meter across it. And if it measures too high, way high, then you know you got bad windings. If it measures real low, then it knows you got shorted windings. And so that's why they usually give it in ohms. So what would our current be? Okay, 16 milliamps. Okay, so I want this guy right here to drop 6 volts at 16 milliamps. So IR1. So I see this is going to be sad. This is the load right here, right? The load, what you're trying to control, like a light bulb or an LED, is sets what you want to do to saturate this thing. But if you apply more voltage, if the power supply available to you is bigger than the one that you have, so this is just like the one with the LED. The LED dropped 2 volts, and I want to turn it on with 5 volts, same circuit. It's just the only thing we changed is that the resistor is giving it and we did this exact same circuit over at motor controls one time. We needed we had a 120 volt source, and we had all we had was a 12 volt relay. Could we do it? Sure. You can take it. All we had to do is see the resistance of the thing and do what? Calculate a resistor, put it in series that dropped all the rest of the voltage. So you'll run into this all the time because in electronics, usually we have standard power supplies. I mean, you have 12 volts, 24 volts, and you don't have somebody making, a 3.3. Well, 3.3 is standard inside computers, but you don't have somebody making what a 33.7853 power supply, right? So what you do is you get what you need, and then you compensate for it later on. I've seen Zeners in a circuit to set the voltage for different devices. So we okay now? So this is IC SAT, so I should have put that right there. So now everything's the same, right? So our one's got to drop. So we got to choose a resistor that drops 6 volts. So R1, it's got to drop 6 volts at 16 milliamps. Huh? That's right. We could have just wrote that down without any math. 375 ohms. That's a good catch, guys. What size would we use? Yeah, we got to be real careful here. This is not saturated. This is what we need to. This is what we need to put in that relay, right? You understand? If it's rated at 306 volts at 370 volts, then it's probably got a range of voltage it was operated at. So what we'd do here is we'd round. That's all, and we won't even check the tolerance, right? You understand? So which way would we round this one? We should round this one up. But if you round it down, it's okay. So you're just putting more current through the transistor than it was the coil than it was designed to handle, right? Does that make sense? You round up to the next standard value. You have, that's all you got, right? With what, 3.9, 3.6? Yeah. Yeah. So that's normally on these guys. So that is not making sure the transistor saturates. This is the one we got to guarantee that makes the transistor saturate. So what we're going to, of course, if you round it up, if you round it down, that's fine. But I'm just telling what you would do out there. So you got a relay, a DC relay. By the way, if it says it's a 6-volt relay and it's DC and you don't know the ohms, what can you do? We got an amazing meter called an ohm meter. It's DC, right? It's not AC. It's not depending on X of L. It's DC. So you can get your ohm meter out and you can measure across the two relay, the contacts to the relay coil, not the contacts, the connections to the relay coil, and measure if it's not specified. So on a DC relay, they might just put you the voltage that's out there. They won't give you the watt. They won't give you the ohms because I know, huh? No, you always round. So if it was below 5, I would round it down to the next value. If it's above 5, I would round it up to the next value. So this is not always. This is just a what? This is just a standard round. What you learned about rounding numbers. So since this is 375, right? Then we would do what? We would round up, because up would be closer to this, which means it would be closer to this, right? You understand? That makes sense. If we round down, it means that now we're way. So if we round down, then more current's flowing through there. It's not dropping 6 volts anymore, right? You understand? So that's what we'd have to figure. So all we're going to do on this guy is we're just going to do what? And what's the rules of rounding? Yeah, so we'd look at this guy. Well, we'd look at that guy first, which means this guy would go to an 8, right? Y'all understand? And then this guy would go to a 4, but we don't have to do that because what's the next? So here we would round up. So it's going to be, do we have a 3.8K? And you don't even have to worry about the tolerance on this guy, right? You understand? Because it's not critical like this guy is right here. So what's the next standard value above 375 ohms? 390. So that'd be fine, 390. That's really, really close. So 3.8 compared to what? 3.9. We're really, really set on this guy. So we'd probably use a 390. Okay. And of course, y'all didn't know, but now you do know, right? So when you're looking at the load, you're looking at trying to maintain the current that is specified to run, right, as close as we can. So we'll round on that guy. Okay, so let's use 390. whatever y'all use. It's going to work out pretty close anyway. So now I calculate IV sat. So I'm going to take, we need to calculate the actual current, right? Which is going to be so close, it's not even going to be. So what's it actually be? So IC sat, yeah, it's about 390. So what is it? Yeah, and what we're going to see, it wouldn't make any difference if you used the 16 milliamp. Then IV sat would be 15.4 milli divided by 30. What? 513 micro. So now we've already going from 16 milli to micro, right? Okay, so this guy right here, we wanted to drop, R2 would be equal to 4.3 volts divided by 513 micro. So what did I do on the key? What did I? Okay. I wouldn't. So what would this be? What would this be? What would R2 be? Okay. Oh, what's that? Yeah, our computed value. 4.3 divided by 513 micro. Yeah, you got to look for your calculator. And one thing you got to understand is if the bottom number is smaller than the top number, we'll never end up with a milli, right? I mean, I'm sorry, but here I got micro down here. Here I got units right here. This is going to be a pretty good size. Yeah, I know, but that's twice you done it. And that's what I'm saying. You need to realize that your answer that you're given is totally wrong if you just understand I'm taking units and divided by micro, right? If the bottom number is small, then my answer is going to be big, right? You understand? And so you'd say, well, I had to do something. You probably heard me do that 100 times. Well, my answer's got to be wrong because I know kind of what to expect. I don't know the answer, but I know it's got to be either bigger or I know it's got to be smaller, right? And so there's some situations where your answer can't be right. So what we got here? Okay. Everybody okay there? And then we're going to round this guy here down because this is the one that assures a saturation. So what are we going to use there? Huh? Okay, 7.5. Then we'll come up and just multiply that by 1.05 just to verify. So we're fine. So 7.5K is the one we'll use. So that's guaranteed, right? You understand? But we come back and we check the tolerance, right? Even though if you use that resistor, odds are it will work, but it won't be guaranteed, right? What's that? Okay. Oh, you're talking about my key, right? Okay, so let me go back to that and correct that for y'all. That was circuit 3, right? Where did I get 5.9 at? Well, see, I did this on purpose so y'all would see if y'all was paying attention. I got the right size, and here we're going up to 390, right? Well, here I got coal. Here I got, what in the world did I do? Okay, any more? So is IB sat? We need to redo that one. Oh, this is the, yeah. So this, but it's going to be close, right? So what do we come up with? 600, 500. What do we come up with IC sat? I'm sorry, IB sat, microamps. How many microamps? 513. What? Okay, got you. And then RB was 9.5K instead of 7.9, right? Oh, okay, going the wrong way. And then what does that come up to be? Okay. And then we use a 7.5. Okay. That look okay, guys? Okay. There's a everything okay? We okay? Any more? Go ahead. Go ahead and take a. Go ahead and take a break. 10 minutes. Yeah, we went over a little while, but so I'll make sure I put the corrected key up on the. Why won't it let me erase that? Oh, there it is. A connection that you're going to run because what's going to happen, you're going to check it on and it's going to check back. It's the way the trends are hooked up inside. So, we call these garden pairs. I got a name from the first person who used it, or probably the first person to explain it. And what we do, if we can the PNP trend, we should, I should, it should be a PNP. But what we do is we take one transistor and then we come over and take the emitter and direct it into the base, and then
sometimes I'm here. How many legs do we need coming out? Three legs. So it's just like our hips. There's not two. So if I come over here and say this is your bigger leg, and I put that sucker on there, some of y'all's meters get regular or LED. If your meter don't turn on LED, your meter will turn on LED. Some of y'all's meters will turn on LED. And now we check all up there. It's just not measure stuff. So, all the on regular. This happened to me. I had a schematic I was troubleshooting, and the dang thing was drawn like that. And when it was about to call the repair. And when I checked it to my meter and I measured it 2 volts between the meter, I did what? It was wrong. And then I finally said, well, we should look at the part. Now, what advantage do we have here? Let's say this thing right here has a beta of 30, and this beta right here has a beta. What would it be called? Beta. It's a gain, guys. Let's most folks think, but let's just take an amplifier down here. Say, okay, this thing gives me a gain of 5. Let's deal with those. So I put 1 volt in, takes 5 volts. Now this guy right here has a gain of 5. I put 5 volts in, I get 5 volts out. So gains are multiplied, guys. They're not added, they're multiplied. So what would the gain be? This circuit would have a gain of 3,000. So, and you put the input resistance, you look at this slot would be a lot. So, man, I could put 1 microamp over here, right? You multiply that by 3,000, right? Garbage and pairs is a lot because you get extremely high gain out of the transistor. The gain before when we turn it on now, both these transistors will saturate. So if I turn this one on, right here, turn on. So it wouldn't work. So the gain, we got a good gain the other way, right? But not here we have the biggest gain. These suckers have got so much gain. We have problems. We have to make sure we still hear it. We don't pick it up information. Call it what? Darlington. Yeah. You go up here and look above Demco, and they're in the same packs as the Darlington pairs in the same dang pack to the TO20 bag. So what does TO stand for? What does TO stand for? We've already talked about that. They simply teach it. Outline. This is the package. This package are register packages. It's a 3-pin package. The tab on top actually means USB. Right? What can be inside that thing? Anything that needs repeating. Right? You understand? Anything. So it might be, I see this pack sticking out there, it might be like very certain. So this has got them inside a deal. We call this a deal. It stands for fully package. So people, but we have the same number of pins on this side that we have on that. So the pins are in line, right? All deal. There's CO2, there's CO92. So this is what our 2 and 30 304s. I have those stuff here. It's just dealing with this. This is a Darlington, right? You understand? No, it's not. All there's a thing up on the Blackwood site that shows the most of the standard out. These are JA registered. These are own technology. Look at you. Anybody. All you gotta do is just make your circuit fit inside that back. And they got there, so TO3, big guy.